Okay, we're still talking about concavity and curve sketching. We want to talk about the second derivative test for local extrema. Suppose that your second derivative is continuous on an open interval that contains x equals c. If f prime of c is 0 and f double prime of c is less than 0, then f has a local maximum at x equals c. So that's saying if the slope of the tangent line is 0 and it's concave downward, then you have a local maximum. If f double prime equals 0, or f prime of c equals 0 and f double prime of c is greater than 0, then f has a local minimum at x equals c. So if the slope is 0 and your second derivative is positive, so it's concave up, then you have a local minimum. If f prime of c equals 0 and f double prime of c equals 0, then the test fails. The function f may have a local maximum, it may have a local minimum, or it may have neither. Here's some examples. If you look at the graph to the left, your first derivative is 0. So at this top point here, you have a slope of 0, a horizontal tangent line. And f double prime is less than 0, which means it's concave downward. And that gives us a local maximum. Here, f prime is 0, so we have a horizontal tangent. And f prime is greater than 0, so it's concave up, so that's a local minimum. Now we want to sketch the graph of the function f of x equals x to the fourth minus 4x cubed plus 10. Now the first things we want to think about are the first and second derivatives. That will tell us where our graph is increasing, where it's decreasing, where it's concave up, and where it's concave down. So if we start with the first derivative, the derivative of x to the fourth is 4x cubed. The derivative of negative 4x cubed would be 3 times 4 is 12, x to the second. And the derivative of 10 is 0. Now if we want to think about where that is equal to 0, so what would our critical values be? We can factor this by factoring out 4x squared, and we'll have x minus 12. Oh, I'm sorry, x minus 3. 4x squared times 3 is 12x squared. So we're looking at where 4x squared is 0 or where x minus 3 is 0. Now here, divide both sides by 4 and you'll have x squared equals 0. Take the square root and you're going to have x equals 0. Here, add 3 to both sides and you'll have x equals 3. So those are our critical points. Those are the places where our first derivative is 0, and we could have a horizontal tangent line at either one of those places. Now let's look at the second derivative, which of course is the derivative of the first derivative. So the derivative of 4x cubed, 3 times 4 is 12x squared. The derivative of 12x squared, 2 times 12 is 24, x to the first power. And if we look at where that is equal to 0, we can again factor. We'll factor out 12x. 12x times x is 12x squared. 12x times negative 2 is negative 24x. So either where 12x is 0 or where x minus 2 is 0. So divide both sides by 12 and I'll have 0. Add 2 to both sides and I'll have 2. Now these are possible inflection points. This tells us this is where it could possibly change from concave down to concave up or concave up to concave down. Now these are the values that we are really going to concentrate on. So what we want to look at, is what happens at 0, what happens at 2, and what happens at 3. And then we want to think about what happens in each one of these intervals. So to the left of 0, is it increasing, is it decreasing, is it concave up, or is it concave down? Between 0 and 2, is it increasing, decreasing, concave up or down, and so forth for each one of these intervals. Okay. Now if we look for all the values less than 0, our f prime is going to be negative, so it's decreasing less than 0. Now it does not change at 0. Between 0 and 3, it's still negative, so it's decreasing still. So from negative infinity all the way up to 3, this graph is going to be decreasing. For x is greater than 3, it will be increasing. Now then you need to think about what happens for f double prime. To the left of 0, it's positive second derivative, so it's concave up. Between 0 and 2, it's a negative second derivative, so it's concave down. And greater than 2, it's positive, so it's concave up. If you want to think about how they do this, if you'll just take that, like that second derivative, this is our second derivative. And if you'll just plug in any value less than 0, so like plug in -1 or plug in -2 or any value into here, you'll get a positive. Any value between 0 and 2, like say 1, you plug in 1 for x and it'll be negative. And same thing up here, and that should be f double prime. I'm sorry, I wrote f prime, but it should be f double prime. And up here, the way they find these is they just take the f prime, which was 4x cubed minus 12x squared, and they plug in a value less than 0, a value between 0 and 3, and a value greater than 3. And then what that tells you is that to the left of 0, it's decreasing in concave up. Between 0 and 2, it's decreasing in concave down. Between 2 and 3, it's decreasing in concave up. And between 3 and infinity, it's increasing in concave up. So you can just kind of get a general shape of the graph. Now this is actually what the graph looks like if you were to plug this into your calculator and look at a graph. Remember, we found our inflection points to be 0 and 2, and you'll notice that it is concave up and changes to concave down, and then at 2 it changes back to concave up. We found our critical values to be at 0 and at 3. You'll notice at 0 it's not a local maximum or minimum, but at 3 we do have a local minimum. Now, as you're drawing graphs, and I know most people really rely on that TI-83 and 84 calculators now to draw graphs, but if you were to draw a graph completely by hand, you'd want to look first at the domain and any symmetries that the curve may have. You'd want to find your first and second derivatives, and that way you could find what your critical points were and what happens to the left and right of each one of those critical points. That tells us where the graph's increasing and where it's decreasing. Then you'd want to find all the inflection points and determine where it was concave up and where it was concave down. Any asymptotes you'd want to make sure you drew, and then you have to just plot some points. Now luckily we do have a calculator that helps us with a lot of the graphing parts now, but it's still important to understand where graphs are increasing and decreasing, where they're concave up and down. Now, on the PowerPoint, you might want to take a look at this very last slide, slide 319, because it just gives you a big overview of what the first and second derivatives tell us about our functions.